In the last class, you recall we were talking about surface tension, right? That was the end of our discussion about field theory, right? And so in the last class, we got up to thinking about what is the interface between two phases. So for the magnetic system, we could say if you have magnetic order parameter m as a function of position x, then there could be a spin down phase in one region and a spin up phase in the other region. So there's a negative order parameter over here and a positive order parameter over there. And then we did a calculation to say, what is the function m of x that minimizes the free energy? And we got a function which is a hyperbolic tangent that looks like that. Okay? And from doing this calculation, we could extract two kinds of information. Right? And so one kind of information is the width of the interface. That's this correlation length, psi, which is the characteristic length scale over which this m of x function is changing. That's psi. Then we could also extract the excess free energy compared with the uniform phase. That is, compared with the situation in which the order parameter is just uniform everywhere. Right? And this excess free energy is proportional to the system size in the in the y and z directions. Okay? So it's equal to the area in the YZ plane times some coefficient. And this coefficient, well, it has to have units of energy per area, right? So it's what is the energy per area of the interface. And the word for that is surface tension. So this is what we did in the magnetic system. Now, there is, of course, an analog in the liquid gas system. Okay? So if we think about the gas and the liquid, you know that we could set up Landau theory for that. Right, so we could write the free energy as some kind of a power series in terms of the density minus the critical density, or in terms of the volume per particle minus the critical volume per particle. Okay, and then we would have a theory that looks a lot like the theory for the Ising magnet. Right? And so we would get basically the same kind of calculation for minimizing the free energy over the density function or the volume per particle function. And so we could make a plot of that, right? So we could make a plot for the volume per particle as a function of z, where z is the height in a container, say from the bottom of a container up to the top of a container. And so we could say at the bottom of the container, maybe there's a liquid phase, and at the top of the container is a gas phase. And then there would be a volume as a function of z function, volume as a function of z, which would start off at the low liquid volume and go up to the high gas volume. And it would have some shape, something like this, right? So it would also be similar to what we calculated for the magnetic problem, something like a hyperbolic tangent profile. Okay, or this is making a plot in terms of the volume. We could make the same kind of plot in terms of the density. So a rho of z. So it would be a high density in the liquid and then dropping down to a low density in the gas phase. And then the kind of analysis that we've done would make a prediction for the width of the interface. So that would be this kind of a width, like that. And it would make a prediction for the surface tension. Sigma, okay, that is what's the energy of the interface per unit area. Okay. And so this is indeed the way that people usually think about surface tension, right? People usually think about the surface tension for the surface of a liquid, right? So if you have the surface of a liquid, meaning that there's liquid on one side, gas on the other side, there's some energy per area for that. And so, well, here is a specific model for the more microscopic kind of features that lead to this macroscopic property, the energy per area. You might remember that earlier on, we were talking about what happens if you, look inside a container that has liquid and gas in it, right? If you increase the temperature, right? When you approach the critical point, okay? And so I had some illustration where there was a container with gas and liquid, and this is at T less than Tc, right? And then when you raise the temperature toward Tc, the interface becomes fuzzier, more blurred out. And when you go all the way up to Tc, then the interface becomes infinitely fuzzy. So it looks like then there's just one phase inside of the container, right? You no longer can see liquid and gas. And so this goes along with what we've calculated, right? And so the point is that the width of the interface is this parameter psi. Right? And when you approach Tc, that width gets bigger and bigger. And when you get to TC, psi is bigger than the size of the container, right? So that the entire volume of the container is then just one fluid, not differentiated between liquid and gas. Okay, so that is one aspect of what I wanted to do with field theory. And that actually ties into the next chapter that I wanted to get towards. Okay, so the next chapter here has to do with dynamics of phase transitions. And this is an important point for what comes next, because later on, I'm going to be talking about what kinds of materials are in equilibrium versus not in thermal equilibrium. And so thinking about dynamics is really important for making that distinction. Okay, so let's talk about that now. All right, so this is a subject which I sometimes like to introduce with a story. Okay, so for my story, right? So suppose it's late at night, okay, and I'm watching TV. Okay, so I'm sitting in my chair, sitting back, watching TV, and I'm so tired. I'm just about falling asleep in my chair, right? And I should really go to bed, right? But I'm too tired to get up out of my chair, so I'm just kind of stuck here. Can't move. And so even when I should go to bed, I'm just going to watch another TV show. So what I need really is for someone to come along and kick me, right? And say, get up, get out of there, go to bed, right? So if I wanted to, make a plot of my free energy, right, as a function of position, we could say maybe it looks like this. Okay, so here is the chair and here is the bed. Okay, and so you can see that the equilibrium state, right, where I should be is here in the bed, right? But if I am here instead in the chair, I am stuck, right? And so if there's any small fluctuation there or there, well, there's a restoring force that pushes me back into the chair. Okay, so I am not going to be able to get from the chair to the bed by means of small fluctuations, right? What I need is for some, big kick to knock me all the way from out of the chair, right? Knock me somewhere like that, and then I can fall that way into the bed. Okay. So physical systems are like that also. Okay, and so to make a specific illustration of that, let's go back to the Ising magnet. And let's look at the phase diagram. Okay, so you remember there's a phase diagram for the magnet in terms of magnetic field and temperature. Okay. And the phase boundary looks like this, right? That there's a first order phase transition, which ends in a critical point here at TC. So let's think about an experiment like this, okay? So suppose we begin at a point here, and we change the magnetic field to a point there. So we are, yes, just changing the sign of the magnetic field. So in the beginning point, we have a certain negative magnetization, which is the kind of thing that you calculate using, well, that you calculated in the first homework, right? And so this is a point, say, where the magnetization is negative, here, I'm making up a number, 0.85. Okay, and then we're changing the magnetic field to a point where the magnetization is positive 0.85. So in the initial state, we know what the material looks like, right? We know that the spins are mostly pointing down. So in this beginning state, the spins are mostly down, but there's a few up. Something like that, okay? And there is an applied field, which is down, okay? Now, we're making the change to go from the beginning state to the ending state, okay? So that means we're going to change the field. Okay, so I'll erase this arrow and I'll draw a new arrow for the new applied field. But what happens then as a function of time? Okay, that's the question, right? We know what should happen eventually, right? Eventually, we should get to a state where the spins are mostly pointing up, with just a few of them pointing down. But how do you get there, right? In the instant when you first cross the line, and get to that point, the spins haven't had time to change yet, okay? So at some brief moment in time, you have the field pointing up, but the spins mostly pointing down. Okay. So now what happens, right? Well, we know that there are random fluctuations, kind of like Brownian motion. Right? In Brownian motion, a little particle is randomly getting kicked around. Right? Here, for the spins are randomly getting little kicks, and so the spins are randomly flipping at certain times. So if we look at a particular spin, maybe this one, okay, maybe there will be a random fluctuation where that spin changes and now it's pointing up instead of pointing down. Okay, then what happens? Well, this spin now feels an influence of the applied magnetic field. That's a very favorable influence, right? When it flips from down to up, it has a favorable interaction with the applied field. That's good. On the other hand, this spin also feels an interaction with the neighboring spins, which are mostly pointing down. Okay. After it flips, now it experiences these unfavorable interactions with all the neighboring spins. Okay. That unfavorable interaction might be very big. Right? That unfavorable interaction might be enough to make the spin tend to flip back, right? So we'll go back to pointing aligned with its neighbors instead of being aligned with the applied field. We could think about this in terms of the free energy plot also, okay? So remember, we know how to plot the free energy as a function of m at any point in the whole phase diagram, okay? So let's think about this point right there, which is our new point that we're thinking about, okay? At that point, the plot of free energy versus magnetic order parameter looks something like this. Okay, so we know that there are two minima because t is less than tc, right? So there's a minimum there and a minimum there, okay? Because the applied field is positive, the absolute minimum is over here. But the material isn't in this state. Instead, it's in this state over there. So if we have a small fluctuation of just one spin flipping, that would be a little change in the magnetic order. So you're making a change like this, increasing the magnetic order a little bit. Okay? And what will happen is, in order to reduce the free energy, the material will tend to go back. Okay, so it's like me being stuck in the chair, right? That if there's a small change in the magnetic order, you'll tend to return to the local minimum rather than going to the global minimum. So the mathematical word for this, that's what I just said, local min versus global min. The physical word for these kinds of things, this is the stable state, and this is a metastable state. So the stable state is the global minimum of the free energy, right? It's the order parameter that gives the absolute lowest possible value of the free energy. Okay? But a metastable state is a local minimum of the free energy. So it's better than any of the nearby states, but it's not the absolute overall minimum. Okay, so this is to show you, right, that even after we cross a phase boundary like this, the state that used to be the stable state when we were over here is now just a metastable state over there. And we might be stuck in that metastable state for some time. So then the question is, how can we get unstuck, right? How can we ever reach the stable state, all right? How do we get from there over to there? So the way that has to work is there has to be a big fluctuation, right? Not just a small fluctuation that is making a little change in the magnetic order parameter, but a big fluctuation that takes you all the way over the barrier. The way that can happen is if multiple spins flip all at the same time. Okay, so instead of having just a single change, here I'll draw a lot of these guys. Well, I don't know, I'm just drawing a whole bunch of these things. Okay, instead of just flipping one, suppose we flip a whole bunch of them somewhere. Okay, so let's flip a whole bunch of them. So suppose we wait for a big fluctuation to come along so that we flip a lot of them. Okay? Then there's a kind of boundary between what is in the original direction and what is in the new favorable direction. Okay? Now, what you can notice about this is that the spins inside this region are interacting with each other, okay? And so they don't all have neighbors that are pointing down, right? Instead, most of their neighbors are pointing up. So they don't feel the same unfavorable interaction that's tending to make them point down. So this then is the key, right? To make a big cluster of spins in the new state, okay? And the words for this, well, they're different kinds of words. People sometimes refer to this as a nucleus of the new phase, or as a droplet, or a bubble. Okay. So what all of those words mean is a region of the new phase which is surrounded by the old phase, right? That outside here, this is the old metastable phase. And in here is the new stable phase. So this is happening in a nucleus or a droplet or a bubble, whatever we call it. And let's suppose that that region has a radius r. So let's figure out then what is the free energy as a function of r. There are basically two contributions to the free energy. One contribution is we can say we've converted a certain volume from this phase to that phase. That's good, right? That reduces the free energy, okay? So how much does it reduce the free energy? Well, on the free energy plot, we can see it reduces the free energy by this amount, right? Let's call that delta F, okay? So a certain amount of the system has gotten converted from a higher free energy density to a lower free energy density. Okay, so that makes a certain change. Okay, so it makes a change which is proportional to the volume of the nucleus. Okay, so it makes a delta F, a change in the total free energy of the whole system, which is going down. So it's negative. Okay, and it is the volume of the nucleus times the change in free energy density, right? This is the change in free energy density per volume.
Quick question.
Please.
On the previous page, you label the spacing as delta lowercase f. Is that supposed to be delta uppercase f?
The whole plot should be lowercase.
Okay.
That would be better. Okay, the whole plot should be lowercase. And this is a free energy density per volume.
Thank you.
Right. So in the the case where we were working with the Ising model way back in chapter 2, I worked out what is the free energy per spin. Okay, and so we had a total free energy, but it was proportional to n, the number of spins, right? And so then when I divided by n, that makes the free energy per spin, right? Or equivalently, I could say, what is the free energy per volume, which is just the same thing multiplied by a factor of the number of spins per volume, which is a constant. Okay. So that is the free energy difference associated with changing a unit volume from one phase to another phase. Okay. Now we say, let's suppose we change a nucleus from one phase to the other phase. So we get the volume of the nucleus times this delta F, okay? So this has units of volume, this has units of energy per volume. So the product has units of energy. So for the volume of the nucleus, well, let's suppose it's approximately a sphere, right? And so then if there's a sphere of radius r, then the volume of the sphere is 4/3 pi r cubed, right? That's the equation for the volume of a sphere, okay? So this gives us a change in the free energy, which is a negative number of 4/3 pi r cubed times delta F. Okay, so this is one contribution to the change in free energy when we create this nucleus of radius r. I'll call this the delta F associated with the volume. But this is not the only change in the free energy. There is some other unfavorable change in the free energy, which is associated with the interface, with the surface that bounds this nucleus, right? That's because the nucleus is one region where the spins are up, but there's some other region where the spins are down, okay? So if we think about crossing the line from here to there, it's pretty similar to the problem that we talked about last week, where we have a magnetic order parameter that's negative, and then it goes up and it's positive, right? So just as a function of position, we have basically the same kind of thing, okay? We have an interface which is changing from negative spins over to positive spins. Now, it's not exactly the same because, well, because for one thing, the interface is curved, right, instead of being straight. And for another thing, there is an applied field in this problem, and there wasn't in the thing that we did last week. So it's not exactly the same, but it's pretty similar. Okay, and so once again, as in that problem, whenever we are crossing an interface like this, we basically have one of these hyperbolic tangent profiles. So we basically have some interface width psi. So there's a width psi associated with how sharp or fuzzy is the interface, okay? And we have an excess free energy associated with the area of the interface. The area, that is, how much of an interface there is going across, okay? So that makes a delta F associated with the area, which is a positive number. It is the surface area of the nucleus times the surface tension that we've been talking about, okay? So the surface area, this is, of course, an area. The surface tension is an energy per area, and together they give something with units of energy. Okay. So if we combine those things, we get a free energy associated with the area, which is a positive, the surface area of a sphere. So that's 4 pi r squared times sigma. So we can put those two pieces together to get the total free energy of the nucleus. So that is a delta F, which is a function of the radius of the nucleus. And it looks like the sum of those two things, so minus 4/3 pi r cubed times delta F plus 4 pi r squared times sigma. Okay. So let's make a plot of this as a function of r. Okay. So when we want to make a conceptual plot like this, we don't actually have numbers to plot, we can think about what is dominant for small r and what is dominant for big R. For small r, well, we have an r squared term and an r cubed term. Okay? For small r squared is much bigger than r cubed. Okay? So for small r, this plot is going to increase like r squared. It will look like a parabola. So we must have a trend like that. What about for big R? Right? For big R, the r cubed term is much bigger than the r squared term. And this is a negative term, right? It favors large radius, right? So for large R, whoops, wrong pen. Our function must look something like that, right? Heading towards negative infinity. So the only way to connect these things up is if the plot looks something like this. Okay, so there has to be a shape like this where there's a maximum, right? That if you are on one side, your plot's going up, on the other side, the plot's going down. Okay, so that tells us then that if you form a nucleus that is very small, a nucleus like this, for example, it will tend to get smaller. It will tend to go away. But if you form a nucleus that is sufficiently big, it will tend to grow. And the borderline between those things is determined by the maximum of that plot. And people call that the critical radius. Let's say RC. Right? If we want to calculate that, we just need the maximum of that function, right? And so to find the critical radius, we just want to say that the derivative with respect to r of this delta f must be 0. Okay, so that's the derivative with respect to r of minus 4/3 pi r cubed delta f plus 4 pi r squared sigma is 0. So this is just an ordinary calculus problem. So let's see, minus 4 pi r squared delta f plus 8 pi r sigma is equal to 0. And we can cancel one factor of r, and we get that the critical radius is equal to 2 sigma over delta f. Okay, so it depends on the competition between the surface tension, that is the energy per area, and the free energy that's gained by converting a volume from the old phase to the new phase. Okay? And then we'll say for a radius greater than RC, if by whatever thermal fluctuations we form a droplet, a nucleus that's bigger than this RC, then the nucleus will grow. But if the radius is less than RC, the nucleus will shrink. And therefore, we need to form a new nucleus, right? And so we are stuck in the old state until we get at least one nucleus which is bigger than this critical radius. And then it can start to grow and grow and grow more and more, and eventually take over the whole system. Okay? So this makes a dynamic process which goes by the name of nucleation and growth. And this is a very widespread process. It occurs in many different kinds of systems in material science. So it is, a common mechanism for the dynamic process of a phase transition. How do you get from an old phase to a new phase? Okay, I'm going to stop talking for now, and I'll discuss more aspects of this on Wednesday. For now, please send me your homework if you haven't done so already, and I'll be glad to answer any questions about this stuff or the homework or anything else. Thank you.